Okay, in part C, we're going to continue with some additional anomalies, some anomalies on top of the anomalies, if you will, in electron configurations. And these are anomalies that go beyond those covered by the electron filling or order diagram. Even if the fact is that there are some cases where even if you get the orbitals in the right order and you have the right number of electrons in the orbitals, you can actually still end up being wrong, because there are some cases where the sort of the theoretical Aufbau principle derived electron configuration for elements will be different from what you actually find in real life. And these are what we're talking about right here. It turns out that there is some amount of stability to be gained by having all of the orbitals in the valence shell either completely filled or half filled. We knew already, because of the noble gases, that there was a great deal of stabilization to be gained by having all of the orbitals in the valence shell filled, because that's the way the noble gases are, and the noble gases are very stable. And so we figured that that's probably related there. But it turns out that that's also true if all of the orbitals in the valence shell are half filled, as well as being completely filled. And this, in fact, in some cases, there's enough of a stabilization effect going on that electrons can actually rearrange themselves in order to achieve that configuration with all of the valence electron orbitals half filled or completely filled. And it'll be, it takes a certain amount of energy to move the electrons around, of course, but the amount of energy that you gain in stabilization basically cancels out the amount of energy you have to put in order to move the electrons around. So it happens spontaneously, and you end up finding a somewhat different electron configuration in real life than you would expect based on theory. Some of the examples would be elements, for instance, where you have where you would expect to have an electron configuration that ends in, say, D4 or D9. Because, of course, D4 would be just one electron short of having one electron in each of the 5 d orbitals in any given shell, like the third shell in this case. D9 would be just one electron short of having, wait a minute, hang on. Yeah. D9 would be just one electron short of having the d orbitals completely filled. And so just by moving one electron so that the d orbitals are half filled or completely filled will result in a significant stabilization or significant decrease in energy. So one example is chromium, which has 24 electrons. The expected electron configuration based on the Aufbau principle would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. The orbital orbital diagram of the 4s and 3d electrons would be like this. 4s2, so that orbital is filled, and then 3d4 would be 1, 2, 3, 4 electrons filling singly in 4 out of the 5 d orbitals of the third shell. And what actually happens is that one of these s electrons will go into one of the d orbitals, and you will end up with all of them, the s and the d orbitals, half filled. So the actual configuration is 1s2, 2s2, 2p6, 3s2, 3p6, the 4s1, 3d5, which is this. And that is actually more stable than this. Another example would be copper, which has an atomic number of 29, so it has 29 electrons, and you would expect the electron configuration to end with 4s2, 3d9. So the 4s orbitals is completely filled, and then 3d9 would mean that the first 4 d orbitals have electron pairs in them, and the 5th d orbital would have a single electron in it. That's what you would expect based on the Aufbau principle, But in reality, one of those s orbitals will shift up to the d orbitals and fill all of the d orbitals, and that will make it more stable. So the actual electron configuration ends in 4s1, 3d10. So now you actually have a vacancy in the 4s orbital, but all of the d orbitals are completely filled. And that is actually more stable than the theoretical electron configuration. And that happens in basically other elements where you would expect it to have you would expect it to have 4d electrons or 9d electrons in the highest shell number that has d electrons. Okay, so that's another exception to the exceptions. As I've already mentioned, actually, I've been trying to introduce this gradually as we went along. And the electron configuration of an element is very closely related to its position in the periodic table and vice versa. So you can tell a lot about the other if you know one of those things. If you know what its electron configuration is, you can find it pretty easily in the periodic table, either by finding the period and the group number from the shell number and the valence electron number, or you can just total up all of the electrons and find out what atomic number it is and look for that atomic number. If you know where an element is in the periodic table, you can go the other way around and tell a lot about its electron configuration. You can, from its group number, if it's in one of the A groups, you can tell, or actually even if it's in one of the transition elements, you can tell how its electron configuration ends from its group number and also from the period number that it's in. And then you could just fill in everything before that, and you've got its electron configuration. Okay, so as I said before, when Mendeleev arranged the known chemical elements at the time so that the elements with similar properties were in vertical columns, one atop the other, with the lightest ones on top and the heaviest ones on the bottom, he didn't know at the time, but it turned out that he was also arranging the elements according to electron configuration, particularly according to the number of electrons in the outermost shell of electrons, which, as I mentioned before, are the ones that are involved in bonding. And so they are responsible for most of the chemical properties of an element. So similar number of valence electrons usually means similar properties. And that's because only the valence electrons are involved in chemical reactions and bond formation. For the main group elements, the number of valence electrons is the same as the group number, that is for the A groups. And the main group elements in the same group will have very similar properties. Like if you look at, say, lithium and sodium, they have very similar properties. They're both very reactive metals. They both form compounds in a 1-to-1 ratio with halogen elements like chlorine. Lithium chloride is LiCl, sodium chloride is NaCl, so they both have a 1-to-1 ratio. If you look at group 2, beryllium and magnesium are very similar to each other. They're lightweight, very reactive metals, although not as reactive as lithium and sodium. They form compounds in a ratio of 1-to-2 with halogens like chlorine. So it's beryllium chloride is BeCl2, magnesium chloride is MgCl2, and so on. And so there are very many similarities in the elements going down a column for the A groups. And that's, of course, because they have the same number of valence electrons. In group 1A, lithium and sodium and potassium and all of the others have one valence electron. And that's why they form in a 1-to-1 ratio compounds with chlorine, for instance, because chlorine in its compounds, with metals anyway, when it forms an ion, chlorine will have a charge of -1. Because sodium, for instance, has one valence electron, it will form an ion by losing that one valence electron and become a cation with a charge of +1. So if you have a +1 and a -1, they will combine with each other in a 1-to-1 ratio. But since all of these other guys in group 1A also have one valence electron, they will also form ions by losing that one valence electron, and they will also have ions with a +1 charge, and therefore they will also form compounds in a 1-to-1 ratio with something like chlorine. In something like magnesium, magnesium is in group 2A, so it has 2 valence electrons, and being a metal which doesn't have a very firm grip on its valence electrons, it will tend to lose those 2 valence electrons when it forms an ion, and it will become an ion with a charge of +2. And therefore, it's going to take 2 Cl minuses to cancel out the positive charge on Mg +2. So you'll find magnesium chloride being MgCl2. And all of these other guys in group 2A also have 2 valence electrons, and they will also lose both of those valence electrons when they form an ion. And so they'll have ions with +2 charges. So they will also form compounds in a 1-to-2 ratio with something like chlorine. BeCl2, MgCl2, CaCl2, SrCl2, and so on. And so that's how a lot of the chemical properties of the elements depend on the number of valence electrons. And at least for the main group elements, the number of valence electrons is the same as the group number. And so if they're in the same group together, they will have very similar chemical properties. And ultimately, that's because they have very similar electron configurations. Okay, let's see, for the main group elements, the A group elements, the last electron in the electron configuration, if you do it according to the Aufbau principle, will enter an s orbital if the element is one of the ones in the s block, which is the first 2 groups on the left, 1A and 2A. Or the last electron to enter, according to the Aufbau principle, will be in a p orbital if the element is in the p block. That's groups 3 through 8A. That's these elements over here. And again, that's why we call it the p block. Oops. For the main group elements, the valence shell is only the highest number shell. So all of the orbitals with the highest principal quantum number would be considered to be the valence shell. And the number of valence electrons would be all of the electrons in orbitals with the highest value for n. And any other electrons would be considered not valence electrons. Any electron that's not a valence electron would be called a core electron. Okay. For the transition elements, where we call the D block, the last electrons added according to the Aufbau principle will enter the d orbitals of the next to last shell, or n-1, the n-1 shell. For the transition elements, the n-1 d electrons are considered to be part of the valence shell along with the ns electrons that were filled right before them. So again, we mentioned for scandium, the electron configuration for scandium would be the same as the configuration for argon, followed by 4s2, 3d1, because the d electrons would be in the n-1 shell. So for scandium, that 3d electron would be considered to be a valence electron, and so would the 4s electrons. So according to the way we account for transition elements, scandium has 3 valence electrons, 4s2 and 3d1. All right. Also, the book points out, and we're not really going to make much of this, but I'll mention it just in passing since the book does. Technically, any element with filled d orbitals in the valence shell is not considered a transition element, according to the official rules of the International Union of Pure and Applied Chemistry. They basically, these are guys who meet every so often, and I think IUPAC is really just an excuse for holding conferences in places like Switzerland and so that they can get paid by the organization to attend. But anyway, they make up all the official rules for chemistry, and some of them get so technical that they aren't really followed on an everyday basis, and this is one of them. According to this rule, zinc and cadmium and mercury, and also copper, silver, and gold would not be considered transition elements, because zinc and cadmium and mercury are in positions where you would expect the electron configuration to involve D10 for the n-1 shell. So for example, for zinc, you would expect the electron configuration to end with 4s2 and then 3d10. For cadmium, you would expect the electron configuration to end in 5s2 followed by 4d10, because cadmium is the 10th element along in the D block. And for mercury, you would expect the electron configuration to end in 6s2 followed by 5d10. So by this official IUPAC rules, zinc, cadmium, and mercury would not qualify as transition elements. In addition, since that rearrangement we talked about in the last segment of the video occurs, and elements that you would expect to have a configuration of 9d electrons, or D9, according to the Aufbau principle, will actually steal an s electron to become D10. That would mean that in practice, copper, silver, and gold would not qualify as transition elements either. And that's a pretty good chunk of the transition elements. So in practice, we're going to call them transition elements, even though the official rules say we shouldn't. The inner transition elements, that is the F block elements down at the bottom, if you look at the atomic numbers for the transition elements, you'll notice that 58 through 71 actually fit into this space here between lanthanum and hafnium. 57, and suddenly it jumps to 72. Some periodic tables make that fairly obvious and some don't. The one I'm using right now didn't, so that's why I penciled in this black line between lanthanum and hafnium and drew the little arrow going down here showing you that, wait, there's a bunch of other elements that actually belong in there. This other periodic table does actually show a gap there, and that gives you a clue that there's something missing, which would be these elements here. So the periodic table really should be drawn with all of these elements here in that space there. Of course, if you did that, it would make the periodic table enormously wide. And in order to fit onto a normal size sheet of paper, you would have to miniaturize things so much that it would be really hard to read. If you Google periodic table and look at the images, you'll see a lot of periodic tables that actually are arranged with the F block elements in place in this spot here. And you'll see those periodic tables really are ridiculously wide. And so that's why they sort of cut them out and put them down here. Also, these are mostly elements that we don't use very often. So it's kind of lucky that we can sort of shove them off to the bottom here, off by themselves, and without losing very much in terms of, understanding of how things are. Anyway, these are known as the F block because this is where the electrons start filling the F orbitals of the period number -2. So cerium, the electron configuration would end with 4F1, and praseodymium would end in 4F2, and so on until you get to 4F14, and then we come back up here and start filling with the d orbitals again, the d orbitals for n-1. And the same with thorium through lawrencium, I think that is. Yeah. So it'd be the same for those, only it would be 5F1, 5F2, 5F3, and so on. Okay. So that's why they're known as the F block. Now, electron configuration of ions. We know that we have electron configurations of atoms, but what about ions? Remember, ions are formed when an atom gains or loses electrons. And that would be a monatomic ion. Of course, there are also polyatomic ions where a molecule basically gains or loses electrons. But we're concerned here mostly with monatomic ions because we don't normally do electron configurations for polyatomic ions. All right, so we'll consider an ion for our purposes in this chapter as being an atom that gains or loses electrons. If an atom gains electrons, it becomes an anion with a negative charge. If an atom loses electrons, it will become a cation with a positive charge. And also keep in mind that it's the metals over on the left-hand side of the periodic table, essentially these elements over here, that tend to lose electrons and become cations, while the nonmetals, the elements in the upper left-hand or upper right-hand corner, will tend to gain electrons and become anions. Except for the noble gases, which don't want to do anything. Okay, so for the main groups, the first electron lost to form a cation will just be the last electron added according to the Aufbau principle. So for the main group elements, last in, first out. The first electron added forming an anion will go wherever the next electron would have gone if you were doing an electron configuration for an atom that has one more electron. So whatever the next lowest energy position is, according to the Aufbau principle, that's where the extra electron goes. If you have an anion with a charge of -2, then that means you've gained 2 electrons, and so the next 2 electrons would go wherever they would go according to the Aufbau principle. So just keep following the Aufbau principle until you've got the number of electrons in the element, and then just add 1 more for each negative charge. So if it's negative, if the charge is -1, add 1 more electron according to the rules of the Aufbau principle. If it has a -2 charge, add 2 more electrons according to the Aufbau principle. For the transition elements and the inner transition or F block elements, things are a little different. The first electron would be removed to form, a cation will come from the s orbital with the highest shell number, not necessarily the last electron in. So for example, for scandium, as we're adding electrons to form scandium, we would add electrons for all of these full orbitals, so we end up with the electron configuration of argon. Then we would add 4s2 and then 3d1. If scandium loses 1 electron to form a +1 ion, it would not be the last electron in. It would not be the 3d electron. It would be one of the 4s electrons that you lose. And if scandium has a charge of +2 for an ion, then you would lose the other 4s electron also. And you don't lose that 3d electron unless you get up to a charge of +3. You'd have to lose 3 electrons before you end up losing any d electrons. And it's the same with the other transition elements. Essentially, for a transition element, if the transition element has a charge of +1, the electron lost will be in the s orbital of the highest number shell. If the transition element has a charge on its ion of +2, then you lose both of the s electrons in the highest number shell. If the transition element has a charge of +3 or higher, then you lose both of the s electrons in the highest number shell, and then you would also lose some d electrons in the n-1 shell. So for the transition elements, you don't start losing any d electrons until you're up to a charge of +3. Then you start losing d electrons. Okay, then the number of electrons, or the electrons added to form an anion, would, like the main group elements, go in whatever is the next lowest energy position according to the Aufbau principle. So the difference between main group and transition elements really comes in removing electrons to form cations. For anions, they act the same way. It just goes into the next position according to the Aufbau principle. Okay, so looking at the electron configurations of some ions, here, we have sodium. Sodium is in group 1A. So, as we established before, for the metals in the main groups, the most common charge for their ions will be the number of the group. Sodium is in group 1A. So you would expect its ions to have a charge of +1, which they do. And the reason for that can be seen by doing their electron configurations. Sodium with 0 charge, that is the element sodium metal, has an atomic number of 11, and that configuration will be 1s2, 2s2, 2p6, 3s1. So the valence shell has 1 electron in it. You could also look at this as being a neon configuration with 3s1 added to it. The sodium plus ion, when it loses 1 electron, will have the configuration 1s2, 2s2, 2p6. So it's lost its entire valence shell, which also means that it now has the same electron configuration as neon. And neon is very stable because it has all of its shells of electrons completely filled. And this is the reason that sodium forms a +1 ion, because if you take 1 electron away, it now has the same electron configuration as neon, which makes it very stable. Okay, that's basically why atoms tend to form the ions they do. They gain or lose however many electrons are necessary to get to the same electron configuration as the nearest noble gas, because that makes them much more stable. So an Na+ ion is actually much more stable than a sodium atom. Now, phosphorus with a -3 charge, or the phosphide ion. Phosphorus, the element, has an atomic number of 15, which gives you a configuration of 1s2, 2s2, 2p6, 3s2, 3p3, or in other words, the configuration of neon plus 3s2, 3p3. And when you gain 3 electrons, remember, because phosphorus is a nonmetal, it's over here in the periodic table, which makes it a nonmetal. Nonmetals form ions by gaining electrons to become anions. And so phosphorus and the charge on the ion will be group number -8 for nonmetals. Phosphorus is in group 5 because it has 5 valence electrons, 2 + 3 in the third shell. So that's group 5. 5 - 8 is -3. That's the charge on the phosphide ion. So phosphorus -3 will have a configuration of this plus 3 more electrons. So 1s2, 2s2, 2p6, 3s2, 3p6, which means that now the valence shell is completely filled. So that its configuration would now be the same as neon plus 3s2, 3p6. But if you look at the periodic table, neon plus 3s2 and 3p, 1, 2, 3, 4, 5, 6, that's actually the same as argon. So the phosphide ion has the same electron configuration as argon, which is a noble gas, which makes it much more stable, which is why phosphorus has a charge of -3, because it gives it the same electron configuration as argon, which is very stable. So the phosphide ion, P-3, is actually more stable than a phosphorus atom. Aluminum with a +3 charge, this is a little bit different. The book actually does the example of aluminum +2, and I'm not sure why they did that, because I have never encountered aluminum with a +2 charge in my life. But +3 is the characteristic charge that aluminum takes as an ion, which you can tell because it's a metal in group 3A. So it should have a charge of +3 as an ion. Aluminum, the element, has atomic number of 13, which means 13 electrons. So that's 1s2, 2s2, 2p6, 3s2, 3p1, 3 electrons in the valence shell, which happens to be n = 3 also. And that is neon with 3s2, 3p1 added onto it. If you lose 3 electrons from aluminum, you now have 10 electrons, which gives you a configuration of 1s2, 2s2, 2p6, or in other words, neon. So Al plus 3 has the same electron configuration as neon, which makes it stable. And that's why it forms a ion with a charge of plus 3. And lastly, iron. Iron with no charge, that is the element iron, has 26 electrons, and it will have a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. You can see here's iron, and so it'll end with 4s2, and then 3d, 1, 2, 3, 4, 5, 6. All right, so that makes sense. If you form the ion Fe plus 2, you're going to lose 2 electrons. But remember, this is a transition element. So the electrons you lose are not going to be the last ones in. They're going to be electrons from the highest number shell, which is the s electrons of shell number 4. So they're the ones that leave to form the plus 2 ion. So you end up with 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. No 4s electrons at all. Okay. For iron plus 3, which is actually, if anything, a more common ion for iron than Fe plus 2, we would lose 1 more electron compared to Fe plus 2. And now you would go for the highest energy. The electron loss would be from the highest energy orbitals in the highest energy shell. So that would mean the next electron to go would be from the d orbital of shell number 3. And so that brings us to 3d5. So the Fe plus 3 has a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. And actually 3d5 means that each of the d orbitals in the third shell has 1 electron in it. And of course, when the d orbitals are half filled, that adds a little stability to the ion. And so in this case, Fe3 plus is a little more stable than Fe2 plus, and that's why you actually encounter Fe3 plus more often than Fe plus 2 or 2 plus. Okay, so that brings us to the section on periodic properties, which is the final section in the chapter, but it's a fairly long one, so we're not all that close to being done yet. Anyway, that's a little overtime for this part of the lecture anyway, so I'm going to cut it off there, and I'll see you next time. One other thing, though, is if you get to the end of this before later today or tomorrow, remember, we've got exam 2 coming up very soon, either Thursday or Friday this week. It'll be on chapters 3, 4, and 5. I wanted to get that in before we finish chapter 6, because that 6 will be on the 3rd exam, which will be the end of the semester. So that'll be coming soon. It'll be online like the first exam. You'll have several days to do it, so there shouldn't be any rush. Just wanted to let you know about that. Okay, so see you next week.